this first non-trivial term appearing at third order, where you flip basically a loop on the smallest possible loop of this lattice. And so on the pyrochlore lattice, that's a hexagon, where this term basically will take a configuration where the spins alternate around this 6-site hexagon, and it will flip them all so that they alternate in the other direction. Okay, so that's what the leading order effect of quantum dynamics is here, is just to introduce essentially tunneling between ice states where you flip a loop on a hexagon. Okay, so what I want to draw your attention to now is how this kind of effective Hamiltonian can actually be interpreted as a gauge theory, and in particular as a version of quantum electrodynamics. So we can sort of anticipate this just a little bit based on the fact that this model of classical spin ice, this picture of classical spin ice as a sort of tangle of loops, be interpreted as sort of classical magnetostatics as a divergence-free constraint that these loops always have to close. Here, we're going to augment that. We're going to go further, right, and essentially introduce the analog of an electric field. Okay? So this derivation I'm going to show you is going to be a little bit technically complicated, and I'm going to go through it a little bit too quickly, really. But I want to just give you a flavor of how it goes, and then I'll try to convince you by showing you some numerical work that's been done in the past 10 years or so that'll show you that this really is a good description of the physics of this model. Okay, so how do you go from something like this loop split flip term to something like quantum electrodynamics? And so the path here is a little bit complicated and full of a bit dodgy approximations. So I'll try to walk you through it. Basically, the first step here is to rewrite our spin operators in a different representation. So here we have SZ and S plus minus. And here what I'm going to do is I'm going to write them in what's called a rotor representation, where I'm essentially modeling them as an angular momentum in 2 dimensions. Okay, and so this has a total momentum Lz, which here we've written as a number operator n, and then this has a phase theta, which if you exponentiate it, will change that angular momentum by plus or minus 1. Okay, and so this number operator is going to represent the z component of these spins, and then these raising and lowering operators for the spins get represented by the raising and lowering operators for this angular momentum. Okay, on its own, this representation is a bit redundant. Here, the spin, if it's spin 1/2, like it is for our case, can only take 2 values, plus or minus a half, where a rotor, its Lz can take any value at all, go from 0, 1, 2, all the way to infinity. So we have to introduce some kind of constraint to restrict ourselves back to the physical spin 1/2 subspace. Okay, so the way this is usually done is we take our representation here, we rewrite our Hamiltonian in terms of these variables. So that 6-site, that hexagon flip term gets mapped to something relatively simple in terms of these rotors. Basically, you just have a cosine of sort of an alternating sum of these phase variables as you go around the hexagon. And then to force this thing to take only the physical values, this rotor charge to be either, this SZ to be only plus or minus a half, we want to force this rotor charge n to be only 0 or 1. Okay, if you put 0 in here, you get minus a half. You put 1 in here, you get plus a half. So that's what we want to restrict it to. And so the way we're going to do that is we're just going to introduce an energy penalty, put it by hand into the Hamiltonian, a penalty if this thing differs from those values. So here, n minus 1/2 squared, the minimum of that will be either 0 or 1. And so if we make that u large enough, that will penalize things other than n being 0 or 1, and thus restrict us back to that subspace. There's a hand up.
There is a coupling terms for 2 spins. Did you miss that?
Which term?
Page.
That's a constant. Yeah, so there's a constant. We're throwing that out. So there's only this 6-spin term.
Okay. Thank you.
Okay, and you might worry about these ends here that show up, but if we're fixing this constraint, these drop out as well from the 6-spin interaction. Okay.
Yes, thank you.
Yeah. Okay, so this, in principle, if we take this u goes to infinity, this is a perfectly good mapping. It's not clear that it's useful, but it's a perfectly good rewriting of our spin model. The next step in this process is the more technically and geometrically involved one, which is we take these rotor variables and we massage them in a way to make them look like more like a lattice gauge theory. And again, I won't be able to get into the details of this because of this three-dimensional geometry is a bit unpleasant. I could spend 30 minutes just going through how all the definitions and how the lattice curls and all of these things make sense. But the basic idea is you take these rotor variables, which include the rotor charge n and this rotor phase theta, and you interpret them as being length variables on a dual lattice. Okay, and so for the pyrochlore lattice, you have these tetrahedra, and so what we're going to call the dual lattice, that will be a diamond lattice, where instead of considering the sites of the pyrochlore, we consider the centers of each of these tetrahedra. Okay, and so if we consider that diamond lattice, then for each link of the diamond lattice, we can associate one site of this pyrochlore. Okay, so for every nearest neighbor link of this diamond lattice, there's a one-to-one mapping to the sites of this pyrochlore. Okay. So we're going to interpret on each one of these pyrochlore sites, these rotor variables, this n or this theta, as being associated with a link variable, this b or this g, on this diamond lattice. Okay. Then what we're going to do is we're going to do an additional transformation, essentially take a lattice curl of these phases. So you might, for the intuition-wise, you might think, why are we doing this, right? It's because we're trying to represent this Hamiltonian that has this sort of alternating sum around a plaquette. That is sort of a lattice version of a curl in some sense. And so we want to represent that a little more naturally. So instead of trying to write things in terms of this link variable g, which is really just another way of writing this phase, we're going to take a lattice curl of this and define a new field we're going to call E. Okay, and so this is the bit of the ugly bit here, which is the lattice curl on this diamond lattice is on a new lattice, which is the dual of that dual diamond lattice. Okay, and so this is why I'm trying to quickly gloss over most of the details here. If you want to get into the nitty gritty of it, I'd look at this paper down here from 2012 where they go over it in great detail. But suffice it to say, if you take the lattice curl of something on this dual diamond lattice here, you'll end up with a link variable on a different lattice, which is sketched here in these blue by these blue lines. Okay. This is all just rewriting of the Hamiltonian. You're just transforming one variable to the other, and if you do that and you stick that in that Hamiltonian we have on the previous slide, you get this here. And if you stare at this for a minute, hopefully you can see that it doesn't look. It's starting to look a little more like electromagnetism, right? We have a piece in the Hamiltonian proportional to b squared, and then we have this cosine term that has an e in it, right? And so if this b is the magnetic field, that looks just like what you'd have in a Maxwell Hamiltonian. And if this e were small, we could Taylor expand this cosine, right? We'd have an e squared term, and then this would start to look more and more like QED. Okay, and so we're going to make a bit of a leap here. We're going to say we can coarse grain this thing to remove this strict large U limit, so we don't have to worry too much about this constraint. And we're going to assume that we can Taylor expand this cosine and only keep the leading terms in E. Okay, so if we do that, we get a Hamiltonian that looks like this. Here, this is a bit of a leap. So really, we should imagine these couplings get renormalized somehow, right? This coarse graining process is going to, modify these couplings in some way that's not particularly easy to calculate, right? But we can imagine that going from here to here after this coarse graining, we can end up with a b squared term and an e squared term. And we should be able to recognize that as something like the Hamiltonian for electrodynamics, right? So it's on a lattice, and it's on a bit of a complicated lattice, but otherwise it looks essentially the same. One thing we just have to be mindful of is, remember, since we're working in this set of ice ground states, we have to make sure that the states we're considering satisfy these ice rules. And in that case, this corresponds to the sum of these b variables for all the links emanating from one site has to be 0. And again, this is just a lattice version of that divergence of b going to 0 constraint. Okay, so by taking this spin model, mapping it to a rotor model, and then renaming these rotor model variables in a creative way, and then doing some kind of coarse graining, we can map this thing to what looks like a lattice version of electrodynamics. Okay, and this lattice gauge theory here, thankfully, is tractable. lattice gauge theories are just quadratic in their variables. So once you introduce the appropriate gauge bosons, you can just diagonalize them, right? And so by writing this E and this B field in terms of some associate appropriate gauge boson, we can turn this into a quadratic Hamiltonian. We can diagonalize it. Okay. And so if you do that, you get something like this with a dispersion that includes a linearly dispersive mode. So this is the full spectrum on the lattice over here in some plane. I think this is just the HHL plane of the pyrochlore lattice. This is that dispersion, and you can see at the zone center at 0, we have this nice linear dispersing mode. This is our emergent photon. Okay, so through this series of mappings, we've mapped it to a gauge theory. This gauge theory, like electromagnetism, has its own emergent version of light. Okay, and if one does this coarse graining carefully, you can actually extract what that speed of light is in terms of the underlying parameters, and it turns out to be about half of this coupling G that appears in this six spin flip Hamiltonian. Okay, so you might be a little worried about this. We just did a whole bunch of mappings. I said the word coarse graining a bunch of times. I Taylor expanded things without any real justification, right? I ignored constraints. Should we really believe this kind of derivation? The short answer is you probably, on its face, maybe you won't believe it. But fortunately, people have tried to confirm this over the years using sort of less dodgy arguments, essentially comparing the results of these kind of arguments to numerical calculations. And yes, this thing ends up working quite well. Okay, so if you take this model and you do quantum Monte Carlo simulation, and for this model, there's no sign problem. The 6-spin model, there's no sign problem. And so quantum Monte Carlo is possible. There's no issues doing that. And you can compare that to what you would get from this photon model, from this lattice gauge theory. And so here I've showed you 3 plots, one of which is the quantum Monte Carlo. So this is a static structure factor. So we're looking at static properties in the HHL plane. You can see it kind of looks like that classical spinized static structure factor, except the pinch points are kind of missing. And if you compare that to what you would predict from this lattice gauge theory for the same quantity, you can see that these things agree quite well. So if you just assume an infinite size system, you get this nice smooth plot. You see pinch points are missing as before. But if you compare the finite size lattice gauge theory to the finite size QMC, you can see they're almost identical. Almost quantitative, really, right? So this sequence of coarse graining and mapping actually works quite well and reproduces the static properties quite nicely. So statics aren't everything. You can even check dynamics. Is this photon really there, right? So this has also been done. This was relatively recently, just a few years ago. So here they actually did quantum Monte Carlo on the original Ising model plus the transverse exchange. So they didn't even bother to do the perturbation theory. They just went directly to the source, to the original model, and did QMC there. And then they did some kind of tricks to go back from imaginary time dynamics to real-time dynamics. And from there, they were able to access the dynamical structure factor. Okay, and so that's what these top panels are showing. Along some cut and momentum space, they're showing the dynamical structure factor as a function of frequency. These are very low frequencies, and you can see that there's some response here following some dispersion. It's very broad, but following some dispersion here. And if you compare this to what you expect from this photon model, where what you would expect is a sharp photon, it looks like what you have down here. Okay, so other than the fact that it's very broad, this is matching the predictions reasonably well. Okay, so some of this is likely due to limitations in the quantum Monte Carlo itself, right? To do this, they've got to lower the temperature down to the scale where the temperature is below this photon bandwidth, right? And remember, this photon bandwidth goes like the cube of this small transverse exchange. So it's actually a very, very small energy scale. And so going to lower and lower temperatures in quantum Monte Carlo gets harder and harder and harder, right? And so they were actually able only really to go to temperatures of order this photon energy scale. And so that's why you likely see all this broadening. And it doesn't look as sharp as you might expect from the analytical results. Okay, so this photon is really there. there really is an emergent electrodynamics coming out of this model. Is a question?
Sorry, can I interrupt? So this is in 3 dimensions.
Yeah.
And can you explain how do you get the polarization of the photon? You have lambda equal to 1 and 2 before, right? The polarization of the photon. How do you get this?
Right. So these photons are defined in terms of these E and B fields, right?
But here, it seems your E and B are scalar. How do I get
Yeah, but there's scalars on the links of this diamond lattice, right? And so basically for each link direction, you get a different field. So when you coarse grain it, the different fields on the different lengths basically end up being the components of E and B.
Okay.
Yeah. And then, so E and B are vectors, and then, yeah. Okay. Good. Right. So the photon exists. It's in the model, and it's actually well reproduced by this just this coarse graining procedure. Okay. So the next question you might ask, well, that's this low energy physics. We also talked about magnetic monopoles, right? We had these fractionalized things that showed up in the classical model. What do these things do in the quantum model, right? Well, here, the quantum exchange essentially is going to cause these things to hop around. So if I take a configuration of classical spin ice that has of an ice state that has 2 monopoles in it, if I apply this transverse exchange, that means swapping, say, 2 of these spins. What you end up doing is moving this monopole from here over to here, right? This turns back into an ice tetrahedron. This thing will now host the monopole. Okay, so these things hop around, and this actually happens at first order in perturbation theory, and so the monopole hopping is actually quite large. It's actually it's significantly larger than the energy scale of that photon. Okay. So at sort of 0th order in the classical model, you just have some energy cost to create this monopole. So you'd expect some flat band of excitations, right? Now, when we add a monopole hopping, sort of in the very simplest picture, what you might expect is this monopole will now pick up some bandwidth of order this transverse exchange, right? And so this is exactly what they see in the same quantum Monte Carlo simulations. So here they're studying that same model, except instead of looking at very low energies, they're looking at high energies near where this monopole energy cost is. And so that's sort of energies of order 1 in this notation. And what they see is a continuum of excitations. Basically, when you create a monopole, you don't create 1, you create 2, right? You create a pair, right? And that pair can have any center of mass moment, any relative momentum with a fixed center of mass momentum, right? And so you get a whole continuum of states for every wave vector due to the presence of these 2 particles, right? And so you see a nice continuum here in these Monte Carlo simulations. And then this dispersion is essentially coming from the fact that these things are hopping around hopping out relatively coherently with an amplitude which is given by this transverse exchange. And this can be modeled relatively simply as just particles, these monopoles hopping on this diamond lattice, and then you look at what that 2 monopole density of states is at each k, and you get some theoretical prediction for what they should be seeing, and that's these bottom 2 panels. Okay, and you can see that modeling, it matches reasonably well between these 2 things. So really, we do have sort of quantum mechanical monopoles running around a fractionalized continuum of these excitations at finite energy. Okay, so we have photons, we have matter. Last but not least is we need to know what the coupling between the photons and the matter is, and in QED that's set by the fine structure constant. So we have to figure out some way to extract that from our models. So this was actually only done relatively recently, just last year. The trick is kind of cute. Basically, what they do is they consider this process we talked about to change the topological sectors, which is you create a pair of monopoles here, and then you drag them apart, pull one through the periodic boundary and annihilate it, and then you ask what that does to the system, right? We know that creates a flux line, right? A line of a spin that winds around the system, and we interpreted that as giving the system some flux through that hole, right? So here I've sort of drawn the flux lines for these particles as I pulled them apart, and then when I'm done, you've left with a finite amount of flux in that periodic direction. Okay, and so the trick here that they did is essentially to interpret this in two different ways. One is, given electrodynamics, we know if we left the system with a bit of flux in it, we can compute the energy of that state from just the usual electromagnetic Hamiltonian, right? If this was, say, a magnetic flux, you'd have an energy proportional to that flux squared integrated over the whole system, right? But there's another way to compute the energy in this change in this process, which is I took two charges. I took a positive and a negative charge, and I dragged them across the system, right? And these things interact with some Coulomb interaction, and so you can compute the work needed to drag them through the periodic boundaries, right? And so the first part only depends on things like the speed of light, the stuff that appears in this electromagnetic Hamiltonian, but the energy to separate these charges, to drag them across the system, depends on the coupling, essentially the coupling of these charges to the electromagnetic field, okay? So by viewing this process in two different ways, you can actually relate the energy of these flux sectors to the energy, to the coupling constant of the matter to the photons. Okay? So then they did that. They did a simulation, calculated the energies of each of these flux sectors, and then through this relation, we're able to extract what this coupling constant is, right? And so for this speed of light, they found, I told you, it was about half of what this G was, this third order perturbation term. What they find for the coupling term is that it's about 0.2 times square root of that. Okay? From that, you can get sort of the more fundamental version of this, which is this dimensionless fine structure constant. You take E squared, you divide it by C. Let's just set H bar to be 1, right? And what they find is for this 6-spin model, you get a fine structure constant, around 0.1. Okay, so if you remember normal, regular fundamental QED, fine structure constant's about 1%, 1 over 137, right? So this is about an order of magnitude bigger. Okay, so it's electrodynamics, but it's not exactly the electrodynamics we know and love, right? It's a little more strongly coupled. The other neat thing they noticed is if you play with the parameters in the model, you start adding perturbations, you can actually dramatically increase this coupling. You can even push it into the regime where it's thought that QED is unstable. And so this sort of nice condensed matter system where you're getting this emergent QED is kind of an interesting laboratory for exploring actually what happens in strongly coupled gauge theories. Okay, so
I have a quick question.
Yeah.
So what is the tuning parameter they are tuning?
So they actually did two. So one, they added this RK potential. That's the purple curve. So there, they didn't get too strong of a change. But then they added a third nearest neighbor term, a third nearest neighbor RK potential, essentially.
I see.
Yeah. So they're just adding sort of simple terms within this effective model.
I see. So that's
they're pushing
interesting.
it closer to the instability.
Please.
Yeah, that's all. They're just pushing it, trying to push it closer to an instability, right? And so when you go this way towards the RK point, this collapses. But I think this way it might be going towards an ordered phase or something, and so you get different behavior.
I see. Thank you.
Yeah. Okay. That's pretty much all I wanted to say about quantum spin ice. Are there any more questions about that before I talk about Kadav's honeycomb model?
So I question that why don't we expect the excitational gauge to introduce the monopole?
Sorry, say it again.
Why the excitational gauge field, EB field, cannot create monopole?
Which monopole? You mean the magnetic monopole?
Because you show the dispersion with monopole and without that's a linear dispersion. Yeah, this is a gap dispersion with monopole.
So this is the dispersion with the monopoles. So this is the actual the excitations from the monopoles themselves.
So is that monopole from a solitone solution in the
gauge theory? No. So okay, yeah, you have to. This is okay in the usual gauge theory language. This would be the response from the matter fields. Okay, so these are from the charges. So in this language, because they're magnetic monopoles, we call them monopoles. So they're in the gauge theory itself. this lattice gauge theory, there are also, let me call them gauge monopoles, right? Defects in the gauge theory itself that would also appear here because it's some compact lattice gauge theory. Those would be, these are less well understood, but the thought is these are going to be roughly of the same energy scale as these photon modes. And so you would see them sort of here, if you could see them at all. Okay, those are actually less well understood in these models. But basically, the energy scale of the gauge monopoles would be comparable to the energy scale of the photon, right? Where the energy scale of these magnetic monopole is huge, right? So this is of order 1. These are of order, 10 to the minus 2, right? For these in this perturbative limit. Yeah, so those gauge monopoles are definitely there, but they would be near this photon, and I haven't mentioned them at all. Does that answer your question?
Yes, thank you.
Okay. Good. All right, so I wanted to go through another example of a quantum spin liquid, a very different one. We'll see how far I get. I might have to speed up or skip some things as we go. But I wanted to tell you about Kidav's Honeycomb model because it's another system we can understand very, very well analytically. It exhibits all of the same phenomenology, but does it in a very different way fundamentally. And so this is a system, spin half system on a honeycomb lattice. And unlike this spin ice system, it's not frustrated by geometry. So the honeycomb lattice is not geometrically frustrated. If you just had an antiferromagnet on here, there's no issue at all satisfying all the interactions. It's actually frustrated by something else. And B, it doesn't have a clean classical limit to start from. And for quantum spin ice, we started from classical spin ice and we perturbed it. Here, this is sort of fundamentally quantum. We start from a quantum limit from the get-go. Okay. So how does this work? So it's a model. It's a spin 1/2 model on a honeycomb lattice. It's frustrated by anisotropy, not by geometry. Basically, on each bond, you have an Ising interaction. On these blue bonds, it's a ZZ interaction. On these red bonds, it's a YY interaction. On the green bonds, it's an XX interaction. And so the component is different depending on which bond you're talking about. Okay, so on its own, each of these would be fine, but you can't simultaneously have the spins be aligned or anti-aligned along Z and along Y and along X at the same time, right? So the fact that the different bonds want different components to align or anti-align is what causes the frustration. Okay, and so it's still frustrated in that you cannot simultaneously satisfy all the interactions, but it's from more than just the geometry, right? It's the geometry combined with the form of the exchange interactions themselves. And so one reason why this is interesting is that this model is exactly solvable, and it has a spin liquid ground state with emergent Majorana fermion excitations. Okay. And so this might be a little surprising. Usually bilinear spin Hamiltonians like this are not exactly solvable outside of one dimension. But this is why this thing has attracted so much attention in the last 10 or 15 years. All right, so how does this work? There's a twofold, two features that make this thing exactly solvable. The first is that there's an infinite number of symmetries in this model that dramatically reduce the Hilbert space size. So on each plaquette of this honeycomb lattice, you can construct what they call a plaquette operator, which is just a product of a set of components of these spins as you go around. Basically, if you start on one part of this spin, you look at the site and you say, okay, there's a Y bond going up here, an X bond going up here. So for this site, I'll take the Z operator. You go to the next site, it's connected to a Y and a Z bond. I take the one that's not there, the X operator. I go to the next one, you take the one that's not there, the Y operator, and I make a product of these things as I go around the loop. Okay, so I've got this sequence of X, Y, Z, X, Y, Z as I encircle this hexagon. Okay, so I construct this bit of a mess of an operator for each of these hexagons, and what you can show is that not only do these hexagons, these plaquette operators commute with each other, every one of them commutes with every other one, they also all commute with the Hamiltonian. Okay, so these are well-defined conserved quantities, discrete conserved quantities, and they can be simultaneously diagonalized with the Hamiltonian and with each other. Okay, so each one, if you stare at them for a second, you realize will square to 1. And so they have eigenvalues plus or minus 1. And so by specifying the eigenvalues of these plaquette operators, plus 1 or minus 1, we can work in that subspace and then reduce the size of our Hilbert space. Okay, and so for this geometry, there's n. If there are n spins, there's n by 2 of these plaquettes, and so what we end up with is 2n by 2 sectors. The Hilbert space breaks up into 2n by 2 sectors, each of size 2n by 2. Okay, and so this is just specifying whether each of these hexagons for this WP operator, this plaquette operator, has a +1 or a -1. Okay. So this immediately tells you interesting things about the model. First off, just the model with this plaquette symmetry will tell you that it cannot magnetically order. So you know you're going to get something interesting. Basically, what you can show is if I try to take the expectation value of a spin operator, I can stick in the square of one of these plaquette operators. If I try to push this plaquette operator through this spin, you can always choose this plaquette operator in such a way that these two things anti-commute. So we pick up a minus sign. And then because these things are local symmetries, we know whatever the ground state is of the system, you can't spontaneously break them, right? This is a version of Elitzer's theorem. You can't spontaneously break local symmetries, right? So whatever this ground state is, it has to be an eigenstate. It has to have a well-defined value for this WP. And so this should give you a constant here, a constant here. Those will cancel. And so we've just flipped the sign of this expectation. Okay, and so this has to be equal to this, which means it's 0. Okay, so we cannot end up with any kind of magnetically ordered ground state here. And so we know we're going to get something a little bit exotic, right? So for the spin half model, we'll see that that's actually a spin liquid. But this little proof here, these symmetries also apply for spin 1 or spin 3 half, or actually arbitrary S-Kadev models. And it will actually tell you that they have no magnetic order as well. Okay, so how does this exact solution go? Well, it's a bit of a process. Basically, what we're going to do is we're going to take each of these spins and rewrite them in some kind of new representation. In this case, it'll be in terms of 4 Majorana fermions. We're going to write our Hamiltonian in terms of those Majorana fermions, and then we're going to group them together in such a way that we can exploit some of the same commutation relations we had for these plaquette operators, but in terms of these new B and C Majorana fermions. We'll find that these UIJs will actually be conserved just like the Ws, and so we'll be able to reduce this thing to a Hamiltonian with constants and then one set of Majorana fermions that appear quadratically in H. Okay? A quadratic Hamiltonian in Majorana fermions for fixed values of U is solvable. Free fermions are solvable. And so if we can determine what the minimum values of these U are, what the best values of these U are, which sector gives the lowest energy, then all we have to do is diagonalize the Hamiltonian in that sector, and we're done. Okay? So how does this go? So let me just point out why you might want to think about Majorana fermions here. One, we just divided our Hilbert space based on these plaquette symmetries into sectors that are of size 2 to the power of n by 2, right? And so that really starts to jump out at you and think, well, I have about a half a degree of freedom left over for each site, right? And half a degree of freedom per site is something like a Majorana fermion, right? And so we're going to try to write this in a representation that'll make this a little more manifest. And so the one we'll use here is we'll write the sigma operators in terms of a C Majorana fermion here, and then 3 of these B's, 1 for each component of the spin, Bx, By, and Bz. Okay, so each Majorana is a half degree of freedom, right? So we've gotten 4 of them, so that's 2 degrees of freedom, right? And so we need a constraint to get back to our 1 degree of freedom in our spin 1/2. And so we'll add one more constraint here that'll make these spins have all the right commutation relations, which is that the product of all these things has to be 1. Okay? But otherwise, other than this constraint, these are just normal Majorana fermions that satisfy the usual relations. And I will skip that. Yes, I will skip that. Okay, so we can take that representation and stick it in our Hamiltonian. And so what do we get? Well, we're getting a B and a C for each spin. And then this B is going to follow that same pattern for the spin components that we had on the lattice. So on a given bond, an X, a Y, or a Z bond, we're going to get a product of the B's that is X, X, Y, Y, or Z, Z. So that's what's being represented here with this gamma. We're summing over all these different types of bonds. That's the type of bond we're talking about, X, Y, or Z. And then we can just rearrange these things because they anti-commute and group these B's together and these C's together. Okay? So this defines a Hamiltonian on this extended space, right? What we want is essentially to solve the problem with the constraint. So the sort of leap we need to make here is that if we can solve the problem without the constraint, right? And then the constraint, which commutes with the Hamiltonian, if we just take the solution of the problem without the constraint, project it into the physical subspace, that will be our ground state. Okay? So if we can solve our unconstrained Hamiltonian, our ground state is just the projection of that state. So the question is, can we solve this? It doesn't look obvious that we can. It's a 4 fermion Hamiltonian, right? These are generally not always solvable. So thankfully, there's sort of a manifestation, a remnant of this plaquette symmetry that's going to save us here. Basically, like we saw that these plaquette operators all commute with each other, commute with the Hamiltonian. These products of these B's have basically the same property. Okay, so if I construct this product of the B's that appears in the Hamiltonian here, I call that Uij. I put one on each link. You can show, just like those plaquette operators, they all commute with each other. They all commute with this Hamiltonian, and they actually all square to 1. Okay, so all of these things are conserved quantities. And so for eigenstates of this extended Hamiltonian, we can set these things equal to just C numbers, the plus or minus 1. Okay, so they have definite values in any energy eigenstate, which I'll label by this little u ij, which is going to be plus or minus 1. Okay, a little more physically, what we're going to see is these are going to end up being Z2 gauge field for these C Majorana fermions. Okay, how you might see this, basically, if you looked at our representation of this spin in terms of the B and the C, you can see there's a bit of a redundancy here. If I were to, say, put a sign on the C, and I put a sign, let me call it Z, plus or minus 1 on the C operator, if I put the corresponding sign on the on the B operator, the spin itself is unchanged, right? So there's sort of a Z2 redundancy built into this representation. And if we look at what happens to this Uij, if we do this transformation, right, each of these B's will pick up a Z, and so this U will actually pick up the product of them. Okay, so it behaves like a gauge field under this redundancy, under this gauge transformation. And so you can make this connection a little sharper if you look at what happens to these plaquette operators, these product of these spins. If you write them all out, what you can show, in fact, is that they actually end up just being equal to a product of these U operators, and it's a product going around this hexagon. Okay, and so this is exactly a Z2 flux operator that you would have in a Z2 gauge theory. Okay, so these are nice because they're gauge invariant quantities. These WPs are defined in terms of the physical spins, and so we can see we're starting to get this emergent gauge structure like we had for the quantum spin isostates. Okay, so we have a gauge field, but it's static. They all commute with the Hamiltonian. They don't change. And so the fluxes and these link variables all have fixed values, right? So for each choice of these link variables, we have a Hamiltonian that just involves these C's, and this Hamiltonian that just involves these C's, thankfully, it's just a free Majorana Hamiltonian, which we can just diagonalize, right? It's diagonalizing an n by n matrix if we have n sites. And so that's, not an exponentially hard problem, right? It's efficiently solvable. So if we want to solve the full model, we have to look at each sector, each choice of these Uijs, and find the one that has the lowest energy, right? Which pattern of the Z2 gauge field will give free fermions with the lowest possible ground state energy? So you could try to brute force this, but thankfully this was proved. It was proved in the mid 90s by Elliott Lieb that for a problem just like this on the Honeycomb lattice, and actually on a related family of lattices, that the best choice you can make here is just have all these things be uniform. Basically, just set all these Uijs to be 1. Okay, so this is sort of the flux-free sector. Okay, and so what that means is the block of the Hamiltonian, the sector of the Hamiltonian that contains the ground state, is just these Cijs hopping around where that amplitude in front of them is just 1. Right? In this case, I, because they're Majoranas, but that gauge field is just 1. And so you just have free fermions, Majorana fermions, hopping around on a Honeycomb lattice with no bond direction, with no dependence on bond direction. Okay? And so that model is even easier to solve. We can just solve it by doing a Fourier transform. We introduce Fourier transform for each of the sublattices. We go to momentum space. You get the same kind of dispersion you'll get for basically any kind of thing hopping around on honeycomb lattice, which is the same dispersion you'll see if you did the dispersion of something like graphene. And then the eigenvalues are just plus and minus the absolute square of this form factor. Okay? So at that point, we're done, right? We have a free fermion ground state of these Majoranas defined by this spectrum. We've got the ground state of the model. Okay? The dispersion itself looks like what you would expect for particles hopping around on a honeycomb lattice, which is it's two bands, positive energy one and a negative energy one, right? And then these two things meet at zero energy, and then where they meet, they touch at the corners of the Brillouin zone, and they touch at linear dispersive points, forming Dirac cones. Okay, so this is the same spectrum as graphene, the same Dirac cones as graphene. The only difference is these are Majorana fermions. Okay, so the ground state of the spin model, we've seen it has a static, but it has a Z2 gauge structure with a Z2 gauge field, right? And then it hosts matter, which in this case are these Majorana fermions. And in this case, this matter is actually gapless. You know, in contrast to quantum spin ice, where the matter had a gap, here our matter is gapless and has this relativistic dispersion, these Dirac-like cones at the corners of the Brillouin zone. Okay. So that is the Kadev spin liquid. Let's talk a little bit about its properties. So because we have an exact solution at zero temperature, you can also efficiently look at this model at finite temperature. Basically the same strategy we used to find that ground state sector. You know, we found the minimum energy configuration of these length variables. If instead of finding the minimum, you just sampled them and then weighted them, you know, by Boltzmann factor, by their energy, you can do Monte Carlo on these things. Okay. And so you can extract finite temperature properties without any trouble doing a kind of quantum Monte Carlo simulation. And so this has been done. So basically we're sampling the flux sectors. For each flux sector, we're solving the fermionic problem in that sector, and then we're doing normal Monte Carlo on top of that. And you can extract things like thermodynamic properties, the energy, the heat capacity, and the entropy. And so I want to point out two features here. One, this heat capacity has two distinct features in it, which is a hump at temperatures of order of this Kadev coupling, this exchange, and then another hump at much lower energy. And then the entropy shows the characteristic feature, which is, you know, because you're releasing entropy here, there's sort of a mild plateau in between, and then it drops further after that. Okay, so what's going on? So here we basically have two classes of excitations. So one, we saw the ground state sector was described by these gapless Majorana fermions, right? And so this is governed by that graphene-like dispersion. But we also have the static gauge field, which when we change that, we can put excitations into there. We call them flux excitations, and those cost energy as well. And so, for example, these have been computed numerically. And if you put a pair of fluxes in, put in one of these fluxes in, you get an energy cost, which is about 10% of this Kadev coupling, right? You put a pair in, it's a little bit lower because they are attracted to each other. You put in these more complicated figurations, you can compute what that energy cost is, okay? So you have sort of two broad classes of excitations. One are these Majoranas, and two are when I can insert gauge fluxes on these hexagons, right? And so these have a cost on their own, but because the Majorana fermions are coupled to this gauge field, you also change the Majorana spectrum when you stick these two things in, when you stick these fluxes in. And so this basically gives you a picture of this thermodynamics. Essentially, what you're seeing here is sort of two energy scales based on what excitations are basically disordered here. So at high temperature, we just have a normal paramagnet. As we come through this first hump, this first energy scale, basically the spins will fractionalize into these Majorana fermions, but will be at high enough temperature that the flux, the gauge field, is disordered. Okay. As we go lower, the fluxes order and release additional entropy, and then all you have left is the excitations of this flux-free sector. And so at each of these, you expect sort of release of half the entropy, which is what you see when you look at this plateau structure. Okay, so I'm running low on time, so let me go a little bit quickly. Based on these plaquette symmetries, you can actually work out how these spin correlations go. Just like these commutation relations with of the spins with the plaquettes, plaquette operators restricted the average to be 0. It actually also restricts the spin correlator to be nearest neighbor only. So even though it's a spin liquid, even though it has gapless excitations, the spin correlations are actually only between nearest neighbor spins. So this is a bit of a peculiarity of the model, but which is broken when you perturb it, but it's something you can get immediately from this exact solution. If you look at dynamics, because of the structure of the exact solution, this is also something that's not too difficult to compute. Basically, if you take this normal spin, time-dependent spin correlator and map it to this Majorana language, basically what you're doing is adding a Majorana to this ground state, and then also adding a pair of fluxes and evolving this thing in time in this background of a flux, and then removing and then looking at the overlap. Okay, and so this is related to an X-ray edge kind of problem, and so you can actually derive a relatively complete solution to this somewhat analytically. And so if you go ahead and compute this, you get a dynamical structure factor that looks something like this. Okay, and so I want to point out here, as a function of momentum, it's pretty featureless. There is some wave vector dependence, but I hope you can see that it's very broad in energy. Right, you have this sort of continuum of excitations that we've been talking about for these quantum spin liquid states. So if we sort of, since it doesn't depend that much on Q, let's just grab a slice of it and look at it. So you can understand most of these features from this picture. Basically, these spin operators, when they act on the ground state, they always create a pair of fluxes. And so the excitation spectrum shows nothing below the cost to create this pair of fluxes, but below this flux gap. And then above this energy, you're essentially looking at the excitations due to the matter itself, due to these Majoranas. And so the energy scale from here out to here is basically the bandwidth of this Majorana excitations. Basically, that's what's giving this continuum, creating these Majorana fermions. Okay, so I should have about 10 minutes left. Is that right?
Yes.
Yes. Okay. So, sorry for going a little fast there. Whenever I give these online talks, I always misjudge how long it takes for me to say things. So hopefully I've given you an impression of what's in common and what's not in common in these two spin liquids, right? So they both have these emergent gauge structures. They both have these fractionalized excitations. They both have these continua, right, in their excitation spectrum. But fundamentally, they look quite different, right? You know, the description, how we got there, was wildly different from one to the other, right? And so coming off the end here, I just want to sort of call attention to some general features and address how you might look for these things in real materials, what issues might arise, and what might be ways around them. Okay, and so what are these signatures we've been looking for, right? We've been looking for, when we define these things, a lack of magnetic order. We've been looking for this broad excitation spectrum, which we've been interpreting as fractionalization. And we've been interpreting sort of low temperature dynamics, right? These low energy features like this photon as being indicative of a spin liquid state. And one we haven't talked about would be something like a topological response, something coming from, say, these topological sectors, or related to the topology of these fractionalized excitations, that could tell us something about the spin liquid state itself, right? And for each of these, you can, immediately run into problems, right? Where if you say, if I don't have magnetic order, could disorder be playing a role, right? You could ask, if the excitation spectrum is broad, could it be because disorder is broadening it, right? And you can ask the same question about dynamics, right? All of these things sort of have caveats, right? I don't have magnetic order. Is it just because I haven't gone low enough in temperature, right? My excitation spectrum is broad. Is that from thermal fluctuations, right? And further, if you have a broad excitation spectrum, if you have dynamics at low temperature, even if the disorder isn't playing a role, even if temperature is low enough, do we know a conventional system, one that isn't a spin liquid, wouldn't show the same behavior, right? And so these are the challenges you have to get around to really confirm that these spin liquids are there, right? And so the first challenge, I think, is making sure that they're stable, right? That we've gotten close enough to this phase that it's there, right? So stability is something that's very much possible. So for the KDEV model, it's actually stable to pretty much all perturbations except those that break time reversal or maybe inversion. And for quantum spin ice, it's actually stable to arbitrary perturbations. Okay, so any perturbation at all, so long as it's small enough, will not break that state. Okay, but we still do need to worry about energy scales, right? So when we say it's stable, we mean it's stable if the perturbation is infinitesimal, right? And so for KDEV models, that means much, much smaller than, say, this flux gap, right? And this flux gap, if you look at this plot here, it's not of order 1 in this exchange scale. It's way smaller than that. Orders of magnitude smaller than that, right? And so when we say small here, that's what we mean. Small relative to this already reduced energy scale. And you have the same thing in spin ice as well, right? The relevant energy scale wasn't the original coupling or even that original transverse exchange, but the cube of it, right? Which dramatically reduces it. So the window of stability is not as big as one might think. And so the room you have to work with is actually smaller than one might think. And so getting rid of these kind of perturbations can be quite difficult. So, for example, the best candidate we have for a KDEV spin liquid is probably this ruthenium chloride compound. Here, the KDEV exchange is thought to be the dominant piece in its Hamiltonian, but there are other symmetry allowed pieces that will always be there, right? And because this KDEV spin liquid is stable, we know if these can be made small enough, we don't have a problem, right? There'll be a finite window, a finite region in phase space where they're there. But the question is, what is small enough and how big are they, right? And so this is a sketch of the phase diagram in the vicinity of this point, and I hope you can see that, you know, we're talking about a scale of something like 5 or 10% to stay within this liquid phase, right? And then once you get out of that 5 or 10% window, you can end up in just a normal magnetic ordered phase, right? And that's exactly what happens in the material itself. Ruthenium chloride does not show quantum spin liquid ground state, but actually ends up in this ordered zigzag phase where you have ferromagnetic chains that are alternating antiferromagnetically. Okay, so actually getting close enough, even if it's stable, can be a challenge. Another major challenge is disorder, right? The key signature that you want to look for, fractionalization, this sort of blurry, non-dispersive excitation spectrum, broad, indistinct excitations instead of sharp quasiparticles. Disorder can do that too, right? And so this is a material where it's been an issue. Ytterbium, magnesium, gallium oxide. It's a triangular anisotropic magnet. It's layered, but in between the layers, the atoms have charge disorder. So they're atoms with different charges that are randomly placed. Okay, and then this will transfer randomness to the magnetic physics, and this will end up broadening things. So, for example, estimates of the broadening just due to G factors being different are actually reasonably large, right? And so this thing still might have spin liquid behavior. It's really not 100% clear, but the fact that disorder is broadening it out makes it a lot harder to diagnose that firmly, right? How do you disentangle the effects of, you know, quantum broadness from the spin liquid behavior from structural disorder, right? So more broadly, you know, is this structural disorder always really a problem? You know, do we really want to get rid of it? You know, is it always like we have to remove the structural disorder, or can the structural disorder actually enhance the spin liquid behavior, right? And further, how do we distinguish something that's trivially disordered, right? That's just broadened because of disorder, from a spin liquid, which is fractionalized in some sense, but also has a little bit of disorder, right? Where that fractionalization is obscured. And so some of these cases, the answer is not particularly clear, right? So this is an example of a magnet that has disorder. It's disordered. At some point, it actually freezes. It's a spin 1 Heisenberg-like model on a pyrochlore lattice. So this is if this was a classical model, it'd be a Heisenberg pyrochlore antiferromagnet, which is known to have a classical spin liquid ground state. But at high temperatures, medium temperatures here, the inelastic response looks quite a lot like what you'd expect from this classical spin liquid, despite of the fact that it has disorder, right? So is the disorder just weak enough? Is the disorder helping? You know, these are questions, right? So even if we can control that, right? Even if we could somehow say we're going to make our samples incredibly clean, we got rid of disorder, right? You still have to make sure that what you're seeing in these broad spectra really is fractionalization, right? You know, you still need to understand whether continua can come from other directions, right? Is it a genuine spin liquid, or is it something like quasi-particle decay, right? Quasi-particles at finite energy can have finite lifetimes. They can be broadened on their own. Could that explain what you're seeing, right? And so we need better understanding of how that works, right? So I talked about ruthenium chloride, which I told you is in an ordered state, not a spin liquid. But if you look at its excitations at high energy, they're broad and indistinct. They don't look like spin waves, right? Is that just what spin waves at high energies look like in anisotropic magnets? Or is that some remnant of spin liquid behavior, right? It's not clear what the answer is. It's not even clear there is an answer, right? But these are the kind of questions one has to grapple with, right? And they're even ordered magnets where the spectrum looks completely broad and indistinct. This is a pyrochlor ferromagnet, anisotropic ferromagnet, a family of them, a terbium titanate, a terbium stannate, a terbium germanate. They're ordered. They're ferromagnetically, but the spectra just look like nothing. They look broad, right? Is this due to disorder? Is this due to phase competition? Is it some kind of fractionalized ordered phase? You know, these are questions that need answers. Lastly, you can ask about sort of the real sharpest, maybe most smoking gun prediction for topologically ordered phases, right? So if you go back to, say, the quantum Hall effect, right? You know, the way you confirm the quantum Hall effect is to measure the quantum Hall effect, right? It has a topological response, right? It's hard to get quantized responses for things any other way. And so you might hope that spin liquids might have something similar. And so in ruthenium, in the Kadev model, there is an analog to this. So if you add a magnetic field and you include it perturbatively, what it shows up when you do this perturbation theory is it shows up like effectively a second neighbor hopping for these Majoranas. And this second neighbor hopping for these Majoranas actually takes the same form you get in the usual Haldane model for a Chern insulator. Okay, so just like when you add this second neighbor hopping to a nearest neighbor model on a honeycomb lattice like Haldane did, you gap out the Dirac cones, and then the two bands you get are topological. They have finite equal and opposite Chern numbers, right? And so the same thing happens when you put on a very weak magnetic field to the Kadev model, right? So you get essentially Majorana Chern insulator, if you want to call it that, right? These Majorana bands now have a finite Chern number, okay? And so because of this finite Chern number, these things now have chiral, topologically protected Majorana edge modes if you would put them on a finite lattice, right? And so this can give a topological response. And so typically you would see this in something like a thermal Hall measurement, where if you have chiral edge modes, you do thermal Hall, you can't do normal Hall, everything here is neutral, right? There's no charge response at all. If you do thermal Hall, the thermal Hall response divided by the temperature, if you have a chiral edge mode, is proportional to a set of fundamental constants, kb squared, a pi at 6, and h bar, and then the chiral central charge of these edge modes. Okay, so for a single Majorana, that would be a half, right? And so you'd actually get a half quantized response in the thermal Hall, right? And so this would be biggest smoking gun you would look for, right? It's very difficult in anything conventional to get a half quantized response. And so there were some claims a few years ago that they were seeing this in ruthenium chloride in a certain configuration of field. This was a bit of a mystery because we knew it wasn't as close to a Kadev model as you'd want to see this physics. So here you can see this plateau here near the half quantized value. Unfortunately, in the ensuing 4 years or so, this result has not yet been reproduced. There's been a few attempts. Here you can see the plateau is supposed to be here. These are different curves at different temperatures. I don't see much of a plateau on any of these curves. And so it's not clear what's going on there. This was just a particular sample of, it's not clear, right? Some samples show evidence for it, some don't. It's a bit of a mystery at this point. But in principle, this would be the smoking gun. This is what you'd be looking for if you could get a reproducible half quantization of something due to the topological nature of this spin liquid state. Okay, so I started this with 3 questions, and I'm going to give you 3 sort of answers in quotes. So what is a spin liquid? It's a magnet that doesn't order down to 0 temperature and is distinct from a trivial paramagnet. How do we stabilize it? Well, we look for highly frustrated models, usually those with an extensive degeneracy, and try to minimize any perturbations, be it stuff that takes you away from your degeneracy or things like disorder, even things like temperature. And then the last question, how do we detect the spin liquid? You need to go to low enough energy. You need to be mindful of any disorder that's in the system. And then you need to look for fractionalized excitations and, if possible, topological responses. Okay, I'm over time, so let me stop there. And if you have any questions.
Outside of question on the outside or online, please.
So can I ask a question? Yeah, so first I want to thank Jeff for giving a really nice tutorial to introduce this spin liquid topic, because it's really a big topic. And I think your tutorial really point out the 2 very important models that can help students to learn what they are, and also point out important questions about experimental realization and detection. So the question I want to ask is about the quantum spin ice part. So I think the photon mode is pretty nicely analogy with the QED. But how about the matter field? So at this point, the matter field seems to be a bosonic matter field. Are there currently, are there possibility to generalize it to be some kind of fermionic matter field such that we can have the real QED? Are there things like that?
That's an interesting question. That's an interesting question. Offhand, I don't know how you would turn that into a fermionic field. I know there are some proposals which, if you can make these things in some sense into dyons, you'll change the statistics, but I'm not sure those are any really realistic at all. Yeah, my short answer would be I don't know, but yes, that is a key difference that I didn't point out, which is these monopoles will behave like bosons, not like fermions, and so it's different from QED in that sense, in that we're talking about bosonic matter. There's one other difference there, which I might have gone too fast on, which is one key difference here is the order of energy scales is actually different. So in normal QED, and for typical things, matter is slow and light is fast, right? Things aren't moving at the speed of light, close to the speed of light that often, right? And so here we're sort of in the opposite regime, where the photon energy scale is actually low relative to this monopole energy scale, right? And so things are a little bit backwards. So the rearrangements of the spin ice states, which describe this photon sector, are actually happening much slower when the monopole is hopping around, right? Which is backwards relative to normal QED. So there are differences. It's not just a perfect replica of fundamental QED, at least outside of the photon.
I see. Thank you.
So, Jeffrey, very nice talk. Can I ask you a question?
Yeah, please.
It's all about the smoking gun evidence of this spin liquid. As you mentioned, there are challenges for all these experiments, right? Evidence that they may, see this raw feature by disorder or other effects. So, is there any, material which shows spin liquid behavior that is, accepted by almost everyone in the community? I was told that there's a material called herbosmithite, right, on cognac lattice, which shows the spin liquid behavior. And that was probably, as far as I know, the only examples in nature that, that everyone, not, I don't know if this is everyone, but I don't see any objections of this. So what's your comment about this?
Yeah,
So,
my comment would be, yeah, everyone might be a little too much because there's always going to be some dissenter out there. Some of these Kagome magnets do have issues with some disorder. Basically, you get magnetic ions between the layers that can give you trouble. And so I think there is still a little bit of contention about how big of a role those things can play. If I'm remembering correctly, don't hold me to this because I might not be remembering correctly. Herbert smithite is one of those systems that has this issue. So I think there can be a little contention there, but yes, it definitely is a perfect Kagome magnet. Other than it definitely doesn't order. It is one of the more accepted examples, but I think there is. I wouldn't be surprised if you could find dissenters in that case as well. In terms of hierarchy here, let me start with classical spin liquids are a little bit easier to answer the question. Okay, so less interesting than a quantum spin liquid, but in the same ballpark, right? And so I'd say there are for sure classical spin liquids that I think everybody accepts. So the classical spin ices, dysprosium titanate and holmium titanate, I think you would be hard pressed to find someone who would not say those are not classical spin liquids, at least before the point where their dynamics get so slow that they freeze.
Yeah, thank you. Just a follow-up question. So you mentioned this topological features might be the smoking gun evidence for this Kita spin liquid, right?
Yeah.
Yeah, so I wonder if this feature also is a smoking out evidence for other spin liquids, such as spin-on excitations. You know that, if you make this material on a torus, and there will be some degeneracies, right? And that could count the topological signature. So what's your comment about that? Is the topological number the smoking gun evidence for all spin liquids, or just the Mariana spin liquid on the Kita model?
Yeah, so it is difficult to translate. Yeah, so in a theoretical sense, just the topological degeneracy is really one of the defining features of these states, right? But experimentally, it's not particularly easy to access, right? And so you need something that is a little more measurable in terms of some topological response, right? So for the KITAB model in a field, you do have these edge modes, and these edge modes give you this quantized response. But for depending on which state you're talking about, it's not always obvious there is such a thing, right? So like suppose I took the KITAB spin liquid and I did not put it in a magnetic field, right? Then there isn't some quantized response to deal with, right? You'd still have these gapless excitations, and you might see, anomalous power laws in, say, heat capacity or various thermal transport measurements, but you wouldn't have that nice, sharp, quantized response that you would have if you put it in a magnetic field. So, for example, for quantum spin ice 2, it's not particularly obvious how you would measure these topological sectors either, right? For quantum spin ice, you would probably want your best smoking gun feature would be probably to actually try to measure this photon, right? And whatever that means, right? So it could be that you actually try to see it in the dynamical structure factor by going to high enough resolution and low enough energies. It could be that you try to see it in, say, something like heat capacity. You get, as you went to very, very low temperature, you'd see a T cubed in heat capacity due to this photon. You might even try to see it in longitudinal thermal transport. So as you got to low temperature, this would also contribute. The photons would carry heat, right? It wouldn't be quantized. So this is why it'd be a little ambiguous, right? You would say, well, I'm seeing additional heat transport, but that could be anything, right? I don't know it's a photon, right? So I think for this, seeing it in inelastic neutron scattering would really put the nail in the coffin. For when there is a quantized response available, I think that's probably always the best choice to make.
Thank you very much.
Yeah.
Hi, Jeff. Thanks for the very nice talk. So, I think I got some questions.
Sure.
So I got some question about the quantum spin ice part. So you mentioned that in one of the derivation in the Hamiltonian, right, is a cosine term for the electric field. So Can you say a few words about why it is a good approximation to assume the electric field is small, and then so that you can do the expansion? Why assuming electric field is small is a good expansion, is a good assumption here.
Yeah. So yeah, strictly speaking, none of these are good approximations, right? So I'll come back to the electric field in a second, but in some sense, we're assuming this B field is well behaved too, right? So this B field is related to these ends, right? And so it actually should only take two values, plus or minus one, plus or minus 1/2. Sorry. And so when we go from this, when we do this coarse graining, we also basically ignore that constraint as well. Right? We soften this and we say, well, we don't care about that anymore. We're doing some coarse graining, right? If we average over enough spins, over enough space or enough time or whatever, right? That doesn't matter. And we're sort of making the same approximation there on E, right? That, sort of the high frequency fluctuations that would cause this thing not to be small are effectively going to be averaged over when we do the full calculation. And so, to be honest, this derivation is probably not the most convincing one. There is a paper from Claudio Castelnuovo's group in the last 5 years or so. It's a semi-classical approach to quantum spin ice, where they do this a little bit more rigorously. It's not as nice in terms of the mapping. It's not as, as clear a sequence in the gauge theories, but they start from a semi-classical limit with a small parameter. And so it's a little bit more justified in how they get from that original 6-spin model down to this lattice gauge theory. So I think if you're looking for a little bit more of a justification there, I would say maybe look at a slightly different approach to this.
Okay,
I know that's a bit of dodging your question, but that's the best answer I've got.
Okay, yeah, sure. And so because so given this emergent QED, right? So you find there's some linear capitalist photon mode. So just wondering if you add some local perturbation, or do you just gap out those photon, or there's some argument for stability?
So there is an argument for stability. So you can show that this thing is actually stable to essentially arbitrary small perturbations. Right, the gauge symmetry in this effective model will protect the gaplessness of the photon. Yeah, so it's a little hard to see where that comes from. It's essentially the assumption that in this effective model, right, the gauge symmetry is essentially coming from this projection into this ice state. I'm pointing at my screen. I don't know why. These projections into the ice state, right? When you restrict to that degenerate manifold, that's where you get this extra gauge symmetry, right? So long as you can get this effective Hamiltonian, all the terms will have this projection, and so this gauge symmetry will be there, and then this gauge symmetry will protect this gaplessness.
Right. Yeah, but I was confused because if you have a gap topological order, then it's simple to see why. But if you have some gapless states, then it's not very obvious to see why it's stable or not. Because I remember there's some earlier paper by Matthew Fisher and other people. There's some argument to protect this U1 spin liquid, for example. But yeah, just just wondering whether you have anything. Yeah, I kind of forget about their argument. Yeah.
Yeah. Okay, so the gaplessness is protected by the U1 gauge symmetry. So that's statement one. Then the question is, well, could you have other perturbations? I think, okay, my recollection might be a bit off on this as well, but my recollection is it's basically a power counting argument. Stability of the space, right? You're starting with something like this, and then you're just adding sort of arbitrary perturbations in terms of these A's that respect to this gauge symmetry. And you do a normal perturbative stability argument.
Right.
The same thing, actually. It's you do the same thing will give you stability of the Kadev liquid as well.
Yeah, sure. Okay. Yeah. Thanks. Yeah.
Maybe I can add something that I know. So I think one thing about this stability issue is When we talk about gap or gapless, usually we focus on is the matter field is gapped or gapless. But in this emergent QED theory, actually the matter field, like this, the the magnetic monopole and the monopole, they are all gapped. So when you are trying to create some I think the argument is that you have two types of perturbation. One is the perturbation that respect the gauge symmetry, and the other is the one that break gauge symmetry. And if those break gauge symmetry perturbation is included, you need to create excitations that is related to these gap modes. And because of that, those perturbation usually is suppressed exponentially by this energy gap. And for those gauge symmetry respected perturbation, it basically follow the gauge symmetry structure. Then the most relevant terms are basically E squared and B squared terms at leading order, I think. So that's why this phase is photon mode is robust, I think.
Yeah. This is actually, I think, basically just what's being said in this effective Hamiltonian language as well, right? So saying that there are terms that break the gauge symmetry is saying I'm going beyond, reducing to this one effective Hamiltonian block, right? I'm including terms that connect these blocks, right? And then we're assuming that this degenerate perturbation theory can eliminate those effectively.
Yes.
That relies on essentially those terms being passive, right? If they're not gapped, we can't remove them with degenerate perturbation theory.
Yes, exactly.
Right. Okay. Yeah. Thanks.
Yeah. It's good. Just tag team the questions.
Oh, can I have a question?
Yeah.
My question is about the Kitov spin liquid and its relation to real material like ruthenium chloride. So as far as I know, that to describe the real material, that a pure Kitov model is not enough. Therefore, we have to add some terms like anisotropy, spin-spin interaction, or the Heisenberg term. So do you know when applying magnetic field, so how those coupling constants change according to the change in the magnetic field?
Yeah. So statement one, 100%. So the real materials, they have actually even more terms than this. This is just sort of a minimal model. Usually they have a Kitaev term. They have this gamma term as the second largest term. There's usually a J. There might be a second or a third name interaction as well. There's more terms in this realistic model. When you add a magnetic field, this will come in as a Zeeman term. Normally, you would not expect these couplings to depend too strongly on the magnetic field, right? These things are being determined by sort of exchange processes with energies of order EV or so, right? And so the magnetic field is just too weak to really dramatically affect these. That would be the usual statement. Like, there will be some change, right? Like when you put on a field, there'll be some kind of magnetostriction, right? You'll change bond angles and bond lengths, and that'll affect this. But I think the assumption at least has been that that's not significant. Offhand, I don't know anybody's actually computed it. Something like magnetostriction in these. Oh, okay. Actually, I'm not sure they've computed exactly this, but there's a series of papers from Rotor Valenti's group in the last few years where they've looked at magnetoelastic couplings in these materials, and so they might have an answer there, but I'm not sure if they've completely addressed essentially how the magnetic field feeds back into the change of the exchange constants.
Okay, thanks.
My initial guess would be it wouldn't have a strong effect, right? Especially, in these experiments, right? If, say these experiments here, we're talking about fields of order, 10 Tesla at most, right? And so these energy scales, the Kitaev coupling in these materials is something like 5 or 10 MeV, right? And so for a G factor of 2, 10 Tesla is just not that big.
Okay, thanks.
Okay.
Hi, Jeff. Thank you for a nice talk. Can I ask some question?
Yeah, please.
Related to pyrochloride material.
Mhm.
So, in the material, it's related to Epping's question. So if we drop doping, so to introduce some electron, so then is it possible to realize I mean, fermionic material, I mean, coupled to the QED.
Yeah, so issue would be is you'd have to, if you doped an electron into the material, you would have now have fermionic matter, right? But then I think the issue is there is it wouldn't be charged under the emergent gauge field. It'd only be charged under the physical gauge field, right? So the trick there, we need to somehow get in, gauge charges that couple to this emergent gauge field, right? And so you'd have to have some probably interesting spin fermion coupling to get them to actually couple in the way you would need.
I see. And another question is related to U1 symmetry. So how this U1 symmetry is translated in terms of, spin, the symmetry operation in real, in the original lattice model?
Right. So gauge symmetries are essentially coming from constraints, right? So in the original lattice model, what we're doing is we're restricting ourselves to the subspace where the ice rules are satisfied, right? And so the constraint we're putting on is essentially that the sum of the SZs on each tetrahedron is 0. So that's the physical condition that's giving rise to this gauge field.
I see. So is there, so to practice U1 symmetry, maybe it is necessary to maybe practice kind of degeneracy or
do what to the U1? To break. Yeah, okay. So this comes back to what we were saying about why is this stable, right? And so again, this gauge symmetry really only makes sense when we're forcing the system to be in these ice states, right? When you're actually imposing that constraint, right? And so it's kind of a symmetry of our description in some sense, right? That we can restrict ourselves to this block, right? And so, as Yiping said, really in reality, you can have couplings between these different sectors, right? The ice states are coupled to states that violate the ice rules, which are coupled to, more states and more states and more states, right? But the point being is because those states are at finite energy, they can be perturbatively removed, right? And then you can still have this well-defined sector with this sharp ice constraint and thus the sharp gauge theory.
I see.
Right. But if somehow these became low in energy, that coupling became too strong, this can all collapse. But that would be, leaving this liquid state.
I see. So here gauge symmetry actually stabilized by large degenerated states.
Yeah. So this is how this, and in most of these spin liquids, this is what happens. So for the Kitev spin liquid is a bit of an exception. I think it's related to the fact that it's solvable. So you're not starting from some perturbative limit. But in a lot of these cases, this is just how it goes, right? Where you have some highly degenerate manifold, and because of that, restricting to that manifold, you can do that sort of in a arbitrarily tight fashion, right? Where you don't have some sort of quasi degeneracy. You can really just say, I have a small perturbation to these states that are exactly degenerate. That's what lets you define this thing at least perturbatively.
I see. Thanks. Yeah.
Yeah.
Any further question? I have one. I'd like to know, is there any way to estimate the bandwidth of the flux excitation and the bandwidth for the Maillard fermions? Is there a way to estimate that before we do calculation?
Yeah. Well, so in the model itself, you can just compute them. Where did it go? I had it here somewhere. There it is. Right. So here the flux excitations don't have a bandwidth per se. So in the pure Kitev model, the flux excitations are actually static. Okay. So they're not dispersive in any way. And so individual flux excitations can have different energies. Where did I put this? So for example, if I have an isolated flux excitation, I pull two of them very far apart, it has one energy. If I bring them closer together, say nearest neighbors here, it's going to be a little hard to see. if I bring them closer together here, where they're right next to each other, they have a bit of a lower energy, right? So there's a bit of a dispersion in some sense in that flux excitations can have different energies, but one shouldn't think of them as being dispersive or coherent or anything like that. Okay? So they occupy a little bit of a band just because they're a little bit of attracted to each other in a classical way, but they're not dispersive and like a particle's dispersive. For the Majoranas, you can get it from the dispersion itself, from this honeycomb lattice dispersion. This is actually just the density of states there. And so you can see that this bandwidth is something like 6 times this coupling, right? And so for the Kitav, these Kitav magnets, that would just be that K that appears in there. This would be something that's, 5 or 10 MeV.
Yes, thank you.
Yep.
Good question. So that's the answer for question again.